So yeah, as David said, my name is Anita. So I work at Dataiku as a data scientist. And I would say that my role as a data scientist at Dataiku is really to help our customers that use our product called DSS, Data Science Studio, to help them at building their data science project. And today I'm going to be speaking about this application for real-time machine learning. So more particularly, this project I've been working on, which was for basically predicting if a patient had a pneumonia or not based on either chest x-rays. And I think as David mentioned, this project was not like for specific customers. It was more done during my kind of research time. And I kind of wanted to highlight that, I'm not a deep learning expert. This was actually my first classification, image classification project. So I kind of wanted to today to walk you through that end-to-end journey of building that CNN for image classification and make it available through some kind of application to basically everybody. So because this project was actually built in DSS, so Data Science Studio, I kind of wanted to quickly introduce this this software. So it's really an amazing piece of software for end-to-end data science projects, from cleaning and modeling the data through building and applying machine learning, also mining, visualizing the data, to even deploying any projects to production, and even monitoring and adjusting those projects. So that's actually the software I use for this use case I'm presenting today. Now, maybe a bit of context on pneumonia and its diagnosis. So according to the World Health Organization, pneumonia would account for actually 50% of all deaths of children under 5 years old internationally. So in 2017, it killed more than 800,000 kids all around the world. And the thing is, accurately diagnosing pneumonia is actually quite complex. So first, the radiographs need to be reviewed by highly trained experts, and then there is some kind of confirmation through, clinical history, but also vital signals and some additional laboratory exams. So it's quite a long process. But even for the review of the radiographs themselves, it can be actually quite difficult because there are a kind of high number of different parameters that could really alter the images, the radiographs, like, for example, the presence of other conditions in the lungs, such as bleeding, cancer, or even just the positioning of the patient or depth of respiration. So we really need, highly trained specialists to be able to kind of detect pneumonia just on those X-rays as a first phase. And those people are usually really good at doing this, but that's not really the issue. The issue is that there are not so many of them, and they usually have really low availability. So that's why I think there's a huge potential for machine learning to kind of automate that first part, which is the image screening in pneumonia detection, because it could really, help at prioritizing, but also kind of just expediting this first part of the process. Because even if for you and me, it could be really hard to detect anything on a radiograph, for machine learning, it actually looks at the actual value of each pixel. So it's actually kind of easier for an algorithm to do the detection. And actually, such kind of AI-powered solution that do the kind of automated detection already exists. For example, one has been developed by Stanford. But what I wanted to show today is, thanks to the appearance of new models like AlexNet, for example, image classification has become really popular. And I think now it's really accessible to any data scientist with Python skills. So for the rest of my talk today, I kind of wanted to walk you through that end-to-end journey. So starting with some kind of data discovery, overview of the data, and then kind of making this choice between Tensorflow and PyTorch, and then seeing how we can define a CNN architecture. And then there will also be some comparison between transfer learning and also training from scratch. And finally, we see how we can basically expose that model in a real-time application. So let's start actually with the data. So the data I use for this project are actually coming from Kaggle. The data I think were uploaded something like 3 years ago. So if you want to use this same data set, you can just go to Kaggle and look for chest X-ray images pneumonia. So they are coming from the Guangzhou Women and Children Medical Center in China. So the X-rays were just performed as kind of clinical routine exams. So they were not specifically done for this data set and to build some kind of AI task on top of them. But still, there was some kind of review of the different images for this data set. So they actually filtered out all the low quality and really unreadable scans from that data set. And then once that was done, they asked 2 different physicians to actually do the kind of the diagnosis to tell for each image if the person, if the kid, especially because it was kids between 1 and 5-year-old, if he or she had a pneumonia or not. So yeah, let's actually look at 3 different images. So those 3 images were actually provided as context for this dataset. So you can actually find them on the main page of the Kaggle dataset. But basically, it's we kind of picture what are the differences between an X-ray coming from a normal person, one coming from someone that had a bacterial pneumonia, and then the last one for viral pneumonia. So if you look at the first one, so on the left, which comes from someone with no pneumonia, it just depicts like clear lungs without any kind of area of abnormal ossification. Really, like you can't see like anything in particular on that image. Now, if you look at the middle one, it kind of exhibits like a focal lobar consolidation. So if you can see like the white arrows, it's actually located in the right upper lobe. So that's typical for bacterial pneumonia. And then for the last one, you can see more something like a diffuse interstitial pattern in actually both lungs, not just one of them. And this is actually typical for viral pneumonia. So, this context provided on the dataset could suggest that it's quite easy to make the difference between a normal chest X-ray image and pneumonia images. But it's actually not the case. Those images are really clean. They are really clear on what they're showing. But I had to look at the dataset myself and was I can't tell just looking at a pneumonia image if actually someone had a pneumonia or not. So it's really actually more complex than that. So the data was actually already split into train sets, validation set, and test set on the Kaggle page. So the train set had a bit more than 5,000 images, then the validation set 16 images, and the test set 624 images. Now, the thing is, 16 images for the validation set is a quite low number. Especially if you are interested in implementing something like a learning rate scheduler. Having such a small number of images generates a lot of variation in the loss, like some kind of noise, because this number is very low. So because I actually wanted to implement a learning rate scheduler, I actually decided to merge the train set and the validation set, and then do a 90-10 split. So 90% of the data from this merged data set went to the train set. So a bit more than 4,700 images. And then the remaining 10% went to the validation set. So, we had a look at the data, and I would say that we are kind of ready for starting coding something. But the thing is, in deep learning, there are two main libraries, Tensorflow and PyTorch. And so we kind of needed to make a decision on which one we wanted to use. So Tensorflow was actually developed by Google and I think publicly released in 2015. PyTorch, on the other hand, was developed by Facebook and publicly released in 2016. So as you can see on the graph on the left, TensorFlow was originally much more popular, but that's also because it was released before PyTorch. But I would say that because PyTorch was more Pythonic in the sense that if you were building something in PyTorch, it was actually, it just felt as if you were building something in Python in general. So because of that, PyTorch gained like a lot of users very quickly. So really like over the years, so from 2018 and up to 2020, it really gained like many new kind of customers. But then actually in 2019, so end of 2019, TensorFlow 2.0 was released. And that's basically when both libraries became like very similar. So the main change, I think, in TensorFlow 2.0 was that the high-level API Keras was actually integrated into the main API itself. So that made things like really like easier. But also like overall, like the TensorFlow team decided to adopt the most popular feature of PyTorch, and that's really why it became like so similar. So today it's quite difficult to make a decision on which one you really want to use on one project to another. So there are small differences, but I would say that overall PyTorch might be more intuitive because there is this high-level APIs, all those high-level APIs like Keras. There's also the feed function that makes training like fast and easier. Also, for example, for GPU, in TensorFlow, users don't have to specify anything, but with PyTorch, you have to move everything onto the device, but also enable CUDA explicitly. But on the other hand, PyTorch is still like, I think, easier to understand if you code a lot in Python. I think the logic is more similar. So it might actually be easier to learn PyTorch in the end. And also, I would say that overall it might be maybe a bit more flexible than TensorFlow. So for example, a feature that I really like in PyTorch is the fact that you can run your network as you build it. So you can really run it line by line, and it makes things way easier to actually debug. So that's basically why I actually decided to use PyTorch for this project over TensorFlow. Another reason is I had the feeling that maybe PyTorch was less black box in the sense that because you have to define more things by yourself, like the number of input channels, output channels, this kind of stuff, you kind of really need to know what you're doing to make sure that it really works. I also wanted to quickly mention PyTorch Lightning because I just made that discovery when I was trying to make that choice between PyTorch and TensorFlow, and I think it's an amazing framework. So I kind of wanted to share that with you because I think it kind of addresses most of the drawbacks you have when you try to use PyTorch over TensorFlow, basically. But PyTorch Lightning is actually a lightweight structure for PyTorch. And it's more like a style guide. It's not really like a framework in itself. But really the idea of PyTorch Lightning is to structure your PyTorch code to basically abstract like all the details of training. So basically with Lightning, you don't need anymore to define your training loop. You don't need to all the time like try to move everything onto your device, especially if you use GPUs, for example. But overall, it was designed with 4 principles in mind. So the first one was to actually enable maximum flexibility, but also to abstract away unnecessary boilerplate, but still try to make them available if you need them. And also all the systems should be self-contained, so the optimizer, the computation corner, and so on and so forth. And finally, your deep learning code should be organized into 4 categories. So first of all, your research code should go to the Lightning module. Then the engineering code, so actually it kind of doesn't exist anymore with Lightning because it's handled by the trainer. Then your non-essential research code, so for example, loggings, that goes to callbacks. And then the data, so the data should be organized using data loaders, but if possible, also using the Lightning data module. So there's much more to PyTorch Lightning. I just don't want to go too much into detail, but yeah, I just wanted to share that with you because I really like this new philosophy. Also, the code looks way cleaner if you use PyTorch Lightning. And even if I I ran into small bugs, I also still think that it kind of lacks some flexibility if you try to do more, I would say, custom stuff. But it's still, I think, a really great library. I really loved that philosophy, and I think it sounds quite promising for the future, at least for the future of PyTorch, because now for now it's just version 1.1, so there's really room for improvement. So basically now we've made that choice in terms of deep learning library. We're actually ready to start building our model. And to be honest, I think that was really the hardest part of this project, to try to come up with some architecture. Because in the beginning, I kind of didn't want to use any transfer learning. I really wanted to build something and train it from scratch because, as I said, it was my first project with image classification. So I think it's always easier to really learn if you try things by yourself. So the first thing I did actually to kind of get a baseline, maybe something very simple, but because I followed this PyTorch tutorial on Cypher 10 classification, I just decided to use the same architecture and just make it fit basically my data because the number of classes was different. And so I trained that model just to get the first baseline, and I got some first performance results. So recall was quite good, but the precision was really low. So I think I ended up with something like 74% accuracy, which is honestly quite low. So then I just decided to kind of just keep moving with more advanced architectures. I actually had a look at the top notebooks on this Kaggle dataset, especially, it's not a Kaggle competition, so you don't get like the highest performance, but you can at least, select by the number of votes for each notebook. So I kind of look at the 2 top notebooks with the higher number of votes. And they were both, using like really deep architecture with separable convolutions, but really like a high number of layers and stuff. So I just tried to implement the same thing, especially because they were using TensorFlow. So I just tried to reproduce the same thing in PyTorch. And I basically ran into the same issue as they did, which was that the performance on training was really good, but it was clearly like overfitting. So the performance on the test set was like something like a 81% accuracy. But I think it still made me do a lot of progress, make a lot of progress. And then I just followed this principle that any kind of good CNN model follows, which is increase with time the number of output channels, and then your image size overall kind of decrease with time. And so I kind of ended up with this architecture. So starting with a 224 by 224 image, and first like 32 output channels, and then 64, 120 by 256, and so on. But still, this was overfitting. So I added more batch normalization, more dropout as well. And also I really tried different data augmentation strategy, because that's also kind of a solution for overfitting. So this is actually the code in PyTorch, so not the full code, just the one for the model itself. So if some of you are familiar with TensorFlow, it can be like a bit perturbating because it's a bit similar, but it's still kind of different. But as you can see, each time you have to define everything. You have to define the input channel, the output channel, and so on and so forth. Same for the fully connected layers. But you can see there's some batch normalization, max pooling. So let's actually have a look at the performance of this architecture. And I also did some kind of experiment with transfer learning, so we're going to be able to do some comparison. So on the left, you can actually see the performance of this architecture I was showing before on the test set. So really like training it from scratch. And I think the results are pretty good. We got an accuracy of 94%, precision kind of the same, and then the recall is actually higher, like almost 97%. I think this is really what we want, because, well, overall, we always want a good accuracy. But in this kind of case, we really don't want to miss any patients that could have pneumonia. So it's actually better to have a higher recall compared to the precision. Because if you tend to predict that people have pneumonia when they don't have pneumonia, that's fine. Then you just do additional tests and then realize that actually this patient doesn't have pneumonia. But if during the first screening you say that a patient doesn't have pneumonia while he or she does, this could be a real issue because maybe you won't go any further in terms of exams. And as we saw, like this kind of disease can actually kill people. So you really don't want to miss any case. But then, yeah, I did actually a quick experiment with transfer learning. So my idea was like, okay, I'm developing this model in some kind of R&D environment, in the sense that I have no timeline. I'm not asked to deliver anything by any kind of date. I'm just kind of doing it for myself. So I spend actually a lot of time on just, for example, the architecture. But what if tomorrow I'm asked to do the same thing, but more like in real life? So maybe with a very short time frame. What performance could I get in, like, let's say, for example, 1 week? So that's when I got interested into transfer learning, because in 1 week you really don't have the time to try to build your own architecture and do some transfer learning. So to do some training from scratch. The only solution is transfer learning. So I actually took several models coming from Touch Vision, like AlexNet, DenseNet, ResNet, all those kinds of very popular architecture. And I've done some fine tuning. And actually, the best model in that case was ResNet. So they're all already trained on the 1000 class ImageNet dataset. And so as you can see, I got pretty high recall, I would say, almost 96%. But then precision was actually quite low, and so was accuracy. So it's kind of an okay model, but obviously in real life, we could never use this kind of solution for actually doing the pneumonia detection. So I'm not doing a kind of apple-to-apple comparison for transfer learning. Just try fine-tuning, just train on 25 epochs. Didn't really try to optimize anything, but it was just like to kind of get a second baseline in terms of like what kind of performance can I get in just a few days, basically. So now, I have this model. So the one I trained from scratch, I'm pretty happy with its performance. But the thing is, it's still, just some code in Python, so for example, in Jupyter notebooks. And then, I just saved the model in a folder, but it's not really like accessible to anybody. So in terms of, from MLOps perspective, it's not even a solution for now. So we need to find a way to basically move that code, that model from this kind of development design environment to another environment where everybody could basically use it. And so that's when I actually started creating an API, an API service. But let's maybe come back to the concept of API and endpoint before really talking about this API service. So an API is basically a software intermediary that allows two applications to talk to each other and exchange data over the HTTP protocol. So for example, let's say that you want to get weather data from the Google API. So you are behind your computer, in front of your computer, and use this web app developed by Google. And you basically send that request to get those weather data. And the thing is, those weather data are actually stored in a server, but you basically need this intermediary to kind of take the request and then send back a response. And that's actually what we call an API. Now, an endpoint is just single path on the API and is normally contained within an API service. So that's why I actually needed to create an API service. And each endpoint fulfills normally a single function. So let's actually, so this is just a quick screenshot of what the endpoints look like, but let me actually switch to DSS to show you how it works in this platform. So this is the homepage of my project for pneumonia detection. So a project is just a container of all you work on a specific task. Now, if I enter the flow, so the flow is just a visual representation of all your data sets, and kind of the dependencies between them. So you probably won't be surprised, like the first thing we see is the training data, but also the validation data, and then the test data. Now those kind of orange circle with this Python logo, I would say, are actually the Python recipe. So they contain the code to generate actually the models. So I've done some testing, so I basically have two of them. But actually this one actually generated a model that then I saved as a PTH file in a folder. And then you just have the additional Python recipe to just create some additional visualization and metrics. But that's the main thing, this folder with the model. But as I was saying, for now, we are still in this development design environment. And, some of my colleagues, I can give access to this project to some of my colleagues, but it still makes it like quite difficult for them to really use it. So actually the best solution in this kind of cases is to actually move that project, that model from this design environment to the API node. And so you can actually do that from the project itself in DSS. So you just need to go to the API designer. So I'm not going to create a new API service because I already have one there. And basically from there, you're going to create maybe one or multiple endpoints to do a specific kind of function. But in my case, the main one is the prediction one. So you can see actually if I click there, I have actually 3 endpoints, but yeah, the main one is the prediction one. So how does that work? Well, I just import some Python library. So this is actually a Python function endpoint. So I import my code libraries and just Python libraries as well. But actually in the settings, I've basically embedded my folders, my folder that contains the model I generated, like the one with the 94% accuracy. So because it's embedded now, I can basically access it using that folder variable. So that's the first line of the code. Then I just specify the image of the size, the size of the image in general. Then I just kind of define the architecture again and then load that model because it's basically the way it works in PyTorch. You have to kind of redefine the real architecture to then be able to load your saved model. And then I just switch to eval mode because I don't want to update any parameters. I'm just using that model to now do prediction. And this is actually the main part of my endpoint. This is really the function of the endpoint. So it takes as a parameter the image in a bytes format. And the only thing it does is it kind of transforms the image. So just resize it to a 224 by 224 image, just convert it into a tensor. And then it does the forward pass to actually get the prediction. Then I just kind of convert that into one prediction for normal, one prediction for pneumonia. But otherwise, I just return those predictions into JSON objects because usually APIs work with JSON formats. And so, I'm still in the design kind of part of my project, but I can already test this endpoint to make sure it works with providing some image. But normally, as soon as I'm done with my endpoint, with my whole API service, what I do in DSS is I actually push it to the API deployer. Actually, if I switch to that window, we are actually in the API deployer. So the API deployer is some kind of centralized UI where you can basically, manage your fleet of API nodes. That's also where you can deploy new services, monitor the health of your API models and stuff. So you can really do many things, but basically, yeah, your nodes and also your API services. This is a management, I would say, kind of sub-platform. And actually, here is already my API service for this kind of pneumonia predictions, but it actually contains different endpoints, but the main one, as I said, is the prediction one. And you can see that this version 2 has already been deployed. So I deployed the first version, then done some modifications. So I deployed a second version and kind of updated. And that's also where you finally really deploy to the API node, because when you push to the API deployer, you just led to that kind of management UI, but then you still need to push to the API node to finally allow people, wherever they are, to kind of send a request to your endpoint and get back prediction of pneumonia prediction or normal prediction. So for example, if I open my API service, I have my free endpoint, but the main one is the prediction one. And I have this endpoint URL that people can use for sending an image, so X-ray image, and get back a kind of prediction. So a probability that the person has pneumonia, for example. But I think there's still an issue in the sense that, okay, now it's more accessible, but you still kind of need some coding skills to understand how to basically send a request to an API and get back a response. It's not very complicated, but I think it's not still not very user-friendly. That's actually why I decided to create a kind of a web app on top of my project. So if I come back to my project, so this is just actually my project. We were just in the API designer. But if I come back to the home page, I can actually go there and go to web apps. And actually I've created a quite simple web app, just HTML with some CSS and then JavaScript and a Flask backend. So if we just have a quick look at the code, especially the Flask backend. So I'm not going to go too much into detail, but now that I have my API service deployed on my API node, I can actually create a client, so kind of connect to that API node and the specific API service, and then basically send then requests to my specific endpoint. So for example, the one for prediction, and then here send a request, and then here I can kind of get back the response, which is the probability that someone has pneumonia or not. So if we go back to the web app itself, so it's really simple. Basically, the main thing you do is you actually choose an image, whatever it is. I'm actually going to pick one from the test set. So I just upload it. And then in a few seconds, we should get actually two different things. So this is the first thing. So this filter is actually a class activation map. So it's, I would say, it's kind of a simple algorithm. So it actually uses your trained model and then basically look at all the different convolutions and kind of, I would say, average them. So it doesn't exactly average them because it takes into account the weight, but it allows you to basically know where the model focused to make the prediction. So if you look at this filter, basically in red, you have the main areas of focus. And in dark blue, it's where basically the model didn't focus at all to make the prediction because it was not bringing any kind of information. And then right below, you get actually the prediction. So in that case, the algorithm is pretty confident that the class should be pneumonia. So it means that the person this X-ray image is coming from as a pneumonia, because this is actually a scale from 0% to 100%. So the probability for normal is very close to 0%, and the probability for pneumonia is very close to 100%. So very simple web app, but at least now you don't need any coding skills. You just upload your image and get your result. So yeah, that's basically everything I kind of wanted to show you today and share with you. But let's actually kind of wrap up. So, we had a look at the data. So coming from this Kaggle data set, and we saw that it's actually really not easy for someone like you and me to detect just from an X-ray image if someone has a pneumonia or not. And some people are really capable of doing that. The issue is that they have really low availability. So that's why there's really I think a huge potential for machine learning to automate that part. Then, I made this choice of using PyTorch for that project because it's kind of, at least in my opinion, it's more flexible than TensorFlow. I really like the fact that I can run my code, my neural network line by line to debug, and also like this kind of less black box model, because as you saw quite quickly, but you saw part of my code, you can see that I need to define the input number of channels, the output number of channels, while usually in TensorFlow you just specify the layer you want, but that's it. And then for really defining this architecture, so yeah, as I was mentioning, I think it's not easy, or at least it was not for me, especially if it's kind of your first or one of your first image classification project, but that's still doable. And it's just, I think, the best way to do it is just to learn from other people. There are so many people out there that know what they are doing. I've been working on deep learning in general, but also image classification project for years. So it's just really useful to just see how they build their own model. And then we just saw kind of a quick comparison between transfer learning and training from scratch. But once again, it was not an apple to apple comparison. It was just kind of getting another baseline of, okay, tomorrow if I have only a few days to build that model, to do something, what kind of performance I can get. And finally, we saw how to move this project from, kind of a development environment to into a real-time application. So by doing basically two things, creating an API service with endpoints, and then basically building a web application on top of the project to use that API service, but kind of behind the scene to just allow people to upload an image and get right away a prediction. But yeah, that's basically it for today. So I guess, do you have any questions?
Wow, thank you very much, Anita. That was fantastic. I think at the start I was like, oh, it's a bit of a side project, but it's very full on, man. It's like, it's been great. It's clearly a fantastic piece of work. So thank you very much for sharing. There have been a few questions coming, but before I get to that, one thing we were trying during the events in November was to have a bit of a virtual round of applause for our speakers. So if you've enjoyed that, please do put a little thank you in the chat, or a little I can't speak today, always going on, hands clapping emoji or something like that in the chat. It would be great to see that coming in. I know you guys are out there. In terms of the questions, if you open up the Q&A, Anita, I'll ask, we'll go through and ask you them, but sometimes it's nice just to read along as we go. So first things first. Okay, the first question I'm going to ask, I've lost who asked the question, but it was basically saying, what a fantastic project. Now, how long have you been working on it? How much work has been involved to get you to the point where you are now?
Yeah, no, that's a good question. The answer is actually not that simple, in the sense that I actually started working on this project on January. But then I was, kind of working on this project like 1 to 2 days a week. And then, sometime between September and October, we got really busy with customers, so I had to stop. So probably like everything together, something like 4 to 5 weeks. Yeah, I would say something like that. Yeah.
Okay. Wow.
But yeah,
you worked very hard in 4 to 5 weeks. So fantastic. Jumping into some of the more technical questions then. We'll take the question there that's coming from Ian Ashmore. Great to see you on today, Ian. Always great to have you with us. Ian's asking, sorry if you've said and I missed it, but were the classes, i.e. pneumonia or not, balanced in the training data? If they were, what insights did your precision versus recall results give you about the model performance? And if they weren't, did you use any sort of strategy to manage this?
No, that's actually a really good question, because it was actually not balanced, and probably not in the way you think, because there were actually more images for pneumonia compared to normal images, which is usually kind of the reverse. So that's a good question, because I actually asked myself the same, like, how do you handle that? Because in regular machine learning, you usually use weights to kind of rebalance, but I wasn't sure if, in deep learning in general, especially neural network, if it was needed. So I actually used both strategy. Like I tried to use no weights and then use weights, so especially kind of rebalancing the loss. And I would say that it actually improved my model using weights, improved my model when I was still kind of stuck with maybe more simple architecture, where I was still kind of overfitting. So it improved the accuracy on the test sets. But when I finally came up with this kind of better model, with maybe slightly more complex architecture, but as you saw, there are not so many layers, weights didn't change anything, actually. It was actually better with no weights.
Okay, fantastic. Thank you. The next question we're going to go to, it's from Ayadua, and he was asking about the difference between training the model from scratch versus using the transfer learning. And he was basically saying, why the option for using a model built from scratch was better than the models on the transfer learning.
Yeah.
And I think you talked a bit on the time that it took, but could you explain a little bit more about that?
Yeah.
Please?
So, well, first of all, I think my comparison is kind of the opposite of what usually you get. Usually you get better performance with transfer learning, whether you're using, fine tuning or feature extraction. But I think, as I was mentioning, I was not doing an apple to apple comparison. For transfer learning, I just trained on 25 epochs, like very quickly, didn't try to optimize anything. It was just like, okay, tomorrow, if you are in a rush, but you're still asked to build this kind of model, what can you get? So I think if I were to start this project over tomorrow and start with transfer learning, I would get like way higher performance. Yeah.
Okay, fantastic. We can jump onto the question there from Zhao Tong. He or she is asking, is this prediction method able to differentiate possible phases of pneumonia?
So that's a good question. So no, it doesn't. For now, it's quite simple. It just basically make a difference between someone that has a pneumonia versus someone that doesn't. But that's a good question, because first of all, I think if you saw, this context slide where you have the three images, so you have normal, but also bacterial pneumonia and viral pneumonia. I think that was kind of my first, I'd say that I was kind of disappointed by the fact that we didn't have this distinction in the dataset, because in the final dataset, you just have normal pneumonia, because the viral pneumonia, I think, is actually way more dangerous than the bacterial pneumonia. So it would have been great to at least, first of all, have a model, but make the distinctions. And then for the stages, no, it doesn't do that. So actually, I don't even know if there is a difference in images if you, I don't know if you have been sick for only 3 days or 1 week, or maybe there is, but I don't know.
Yeah, fantastic, thank you. Question there from Nicholas. What do you think about the Keras library? Should I start learning PyTorch instead?
I think it's not that simple. I think there are many things to take into account that I didn't even mention. Because, for example, like for transfer learning, there are some pre-trained models that exist in with TensorFlow that don't with PyTorch, and kind of the reverse. Also depends if you need to, if you are already thinking of putting that model into production. Can be easier with some high-level APIs from TensorFlow compared to PyTorch and the reverse. So there are many details that you have to take into account when you start your project to kind of make that decision. Overall, I think if you want your life to be easy and it's your first project, maybe go for TensorFlow, so with Keras, because now it's kind of integrated into the main API. But for the longer term, like, I kind of prefer PyTorch.
I had a feeling. We're going to jump to the question there from Bilash. I guess this is a bit more around getting that data to start, being able to train your model and stuff like that. And he was asking, what were the data challenges, and what was the approach that you took to overcome that? I guess using the Kaggle data perhaps helped in that respect. Was there particular data challenges that you came up against?
So yeah, I think you're right. Like the fact that it's a Kaggle dataset means that overall the data are quite clean compared to reality, and that was actually one of my fear. Like, because how does it compare to reality? Like, would this kind of model really generalize well? Because they discarded like low quality and unreadable scans, but is it the way it works in hospital? If they take a scan and see that it's low quality, do they redo a scan, or do they just still use it? And what's also the cost of redoing a scan? So that was my first fear, like, is it like a real life data set, basically? So that was maybe the first point. And then, overall, I think there wasn't like any kind of challenge. Maybe I did ask myself like if I should treat them as 3-channel images or 1-channel images, because you know, they are normally, if you look at them, it's just grayscale images, but some of them will still store as 3-channel images, so colored. And I saw that in most of the notebooks they were actually treating them as 3 channels. So I wasn't really sure what was best, but for me it didn't make sense to do colored. So I switched to grayscale and actually got a quite good performance. So I think it was the right choice.
Sounds good. Sounds good. Kulvinder is asking a question around, you know, future potential in terms of this project, and asking, you know, do you see potential to use this project for other diagnoses beyond pneumonia?
Yeah, definitely. I think probably cancer could be quite similar, because actually, as I was mentioning, one of the factor like kind of altering the image is the presence of cancer in lungs. So I guess this could work the same. I don't know, like I'm not a doctor, like I don't know much in the medical field, but I guess there are many different applications to that. Yeah.
For sure, for sure. And again, it's probably showing my naivety a little bit, but is there software out there? Are there models out there that are quite well known for doing this type of work? And if so, how does your model performance compare?
Yeah, but no, that's a good question. So there are already kind of some solutions, although they're not like so easy to find because I guess they target like a very specific public in hospitals. So that's why it's not like the first thing you find on Google. So from what I also heard from, you know, colleagues working with kind of companies developing this kind of solution, it seems that they get something like an accuracy around 96, 97%, but obviously we call way higher because that's what we want. So something like 99 dot something percent. So I'm not too far from that, obviously, but as I said, I'm not sure how well my model generalized because I just trained it on a specific data set. It might actually even be biased because all those images are coming from the same hospital, so they might actually have been taken by the exact same machine, and this could be an issue. But okay. Yeah,
fantastic. Again, I mean, what you're talking about in terms of, you know, if you get into productionizing this stuff, it brings in lots of different stuff, and that goes into our next question here. And it may well not be something that you've had to consider, obviously, in this project at this point. But the question from JC Babescu, just curious about how you handle security for the people uploading images. Is that something? Is that further down the line? Is that something you've thought about already?
Yeah. So it's, yeah, I guess it's not yet managed to be honest, because my web app is actually currently not public. So only my colleagues working on the same instance can have access to it. But I think it's a really good question, honestly. Security. Although,
key.
Yeah, I'm not an expert, but there are ways to kind of set up some kind of login, you know, a layer. But yeah.
Perfect. And then I've got a couple of questions which I'm just going to kind of bundle up into one, and it's all around training the model. So the questions are, in no particular order, you know, how long did it take to train from scratch? Was that on a local machine or on a cloud provider? You know, can you tell us more about hardware, GPUs, all that sort of stuff? So what did the training of the model look like?
Okay, so first of all, I use a VM. It was not on my machine because my machine doesn't have any GPU. And I think it's kind of the limitation when you do image classification. I don't really see our possibilities to do it without any GPU. So I actually use Amazon Image for that. But basically the GPU associated with it was, I think, NVIDIA, I think Tesla K80, something like that. So not like the fanciest GPU, but a decent one. And for training from scratch on, so for my model, I trained it on 100 epochs, and it took approximately like 40 minutes.
Fantastic. Okay, there's literally stacks of questions, but we're always a bit conscious of time with this actually, and we do try and keep these lunch and learns to 1 hour. What we'll do, any extra questions, we'll follow up with you afterwards, Anita, and perhaps we can turn it into a blog post or something like that.
Yeah.
But just to wrap things up, and it is quite a nice question to finish with, I think, you know, people that are, you know, looking to expand on this further, they're looking to do things like this themselves. Have you got any tips in terms of resources, recommended reading, anything online or published anywhere? What tips can you give in terms of further learning in this area?
Yeah. So maybe on the deep learning aspect, I think that a really great book is the deep learning one from Jan Goodfellow and his associates. So I think this is kind of the basic one. But then for PyTorch more specifically, honestly, the tutorials are amazing. So you just go to their website. Honestly, there are loads of stuff. So for example, on Sci-Fi 10, it really helped me. So there's that. Then on API services, endpoints and stuff, actually more like learn it from colleagues, to be honest, that were just, you know, sitting next to me and showing me stuff around. So don't have any resource for that. And kind of same for the web app. I just learned it from scratch, like just Googling, like doing that in JavaScript, basically.
Everyone needs to come and work with you at Dataiku and get 1 or 2 days a week to work on side projects.
Yeah.
Fantastic, fantastic. But as I say, we will draw things to a bit of a close there. Personally, thank you very much for giving us this talk. It's been a fantastic last session to end the year with, so thank you for doing that. As mentioned, we have lots of big plans for next year, so maybe we'll even get the chance to have you back, or maybe even in person, which would be...
Yeah, hopefully. But yeah, thank you for having me once again.
Thank you very much, and thanks everyone for joining us, and we'll see you next year. Speak to you all soon. Bye-bye.
Bye.